Hello students, in this video we'll discuss the Weierstrass-Enneper representation of minimal surfaces. So if we consider two complex valued functions, f and g, on a simply connected set, omega, with f holomorphic and g meromorphic, meaning it's holomorphic except on the complement of a discrete set, basically. Or let's call it just a finite set, okay? Right? I'm actually going to assume that G only has poles for this to work, right? And then I want one sort of technical condition, right? So if G, here's a technical restriction, if G has a pole of order k at a point z equals z0, then I want f to have a root of order at least 2k. Then f has a 0 of order greater than or equal to 2k. Actually, strictly greater than 2k, right? I want to make it strictly greater than 2k if I want. Strictly greater than 2k at the same point z equals z0. At z equals z0. Okay, so that's a technical condition. Then we can define this function over here, this vectorized function psi of zeta, to be what? To be 1/2 this vector, so it's a vector holomorphic function. It's going to be f, and then it's going to be 1 minus g squared, and it's going to be I, and then f, and then 1 plus g squared, okay? And then what? And then the final thing is just going to be f times g over here, like so, okay? That's my analytic function. Now let's actually check over here. I'm going to call this phi 1, phi 2, phi 3. Phi 1, phi 2, phi 3. And now let's notice the following. So notice that the first thing to notice is that this technical condition over here that we just wrote out ensures what? Ensures that if G has a pole of order k over here, this thing will have a pole of order, G squared will have a pole of order 2k. But when I hit that with f, what's going to happen? When I hit that with f, that's going to give me what? F has a 0 of order greater than 2k, so that's going to eliminate the singularity in the denominator. Same thing over here. This thing over here, this g squared is going to have a pole of order 2k, right? And then this f is going to have a 0 over 2k, so in other words, each of these components over here is analytic, right? So our technical condition, the condition, let's call it condition over here star, condition star ensures that phi is holomorphic in the set omega, right? Good. All right, and so now what I want to check is let's look at this condition that we've seen before, right? It's holomorphic. Furthermore, it's not equal to 0, right? It's not identically equal to 0. Okay. Great. And so now what I want to do is the following. I want to look at phi 1 squared plus phi 2 squared plus phi 3 squared. And what's that going to give us over here? So it's going to give us what? It's going to give us this thing squared over here. So everything's going to have a 1/4. Pull that out of everything. And then I'll have an f squared, and then a 1 minus 2g squared plus g to the 4th, right? And then over here, we're going to have a what? We're going to have a, if I square this over here, I'm going to have a minus f squared and then 1 plus 2g over here, and then plus And I need to actually, if I pull out a 1, I need a 2 here, actually. Let's put a 2 over there. G squared, and then a what? And then a plus G to the 4th. And then a plus 4 F squared G squared over here. And let's see what happens over here. So we have an F squared minus F squared, so those are going to cancel out. We have an F squared G to the 4th, a F squared G to the 4th, a negative, so those are going to cancel out over there. And finally, I have a 2F squared G squared, a 2F squared G squared negative, so I have negative 4 and positive 4, so this equals 0 over here. Beautiful. So these components of the components phi 1, phi 2, phi 3 of the vector psi satisfy this condition over here. So in other words, if I look at this integral over here, so if I define R of u and v to be the real part of the integral over a parameterized curve gamma of what? Of just this vector field psi of xc dxc. We'll define a what? This defines a conformal minimal surface. Okay. And conversely, right? Conversely, if I have a conformal minimal, if I have a vector value function that satisfies this condition over here, what we can do is we can define a pair of functions that will satisfy this equation over here, right? So that conversely, what we can do is, if you think about this carefully, you can also do this. You can also sort of set f to be phi 1 minus I phi 2 and g to be phi 3 over phi 1 minus I phi 2. And if I look at this pairing over here, it's clear that f times g is going to be what? F times g is going to be the phi 3 component, right? And then if I look at this thing squared over here, I'll get exactly phi 2, and then I pull it out because I'm going to have the imaginary part with the I, right? So that's going to give me phi 2, and that will be phi 1, right? So the algebra easily shows us that this is going to be, in other words, if phi 1 squared plus phi 2 squared plus phi 3 squared is equal to 0, then this expression over here, then I can write vector field psi in terms of these two functions up here. So it's an if and only if statement. Okay, beautiful. All right, and so now it's an example of this. So I'm going to do a very, very simple example. I'm going to choose f to be 1. I'm going to choose f of zeta to be 1 and g of zeta just to be zeta. Okay? That certainly satisfies the condition of my theorem, right? There's not even any poles over here. It's a beautiful, just analytic function. Okay? Excellent. And so let's do this construction and see what we get. So then what's our psi going to be? So our psi of zeta is going to be what? Is going to be just a 1/2. And then I'm going to have f, then I'm going to have a 1 minus zeta squared. Then we're going to have a what? A 1 plus zeta squared with an I, so I 1 plus zeta squared. And then finally just a 2 zeta, like so. Cool. So let's integrate this thing, which is formally integrate this thing with respect to xc, and what we get. So therefore, if I look at r of u and v, r of u and v is going to be the real part of the integral of this thing over here. So the integral of this thing is going to be a 1/2 in front of everything. So pull 1/2 out. And then I'm going to have an integral of this thing, which is going to be a zeta minus zeta cubed over 3. And I'm going to assume that my path is going to what? That my path over here is just going to map 0, 0 to an arbitrary point, zeta, right? So that's by definition what we'll have over here. Then we'll have what? Then we're going to have, the next thing over here is going to be a I, and then a zeta, and then plus zeta cubed. And then finally a what? Then finally a zeta squared. Remember that zeta is u plus iv, right? So what's this over here? This is going to be a 1/2, the real part of what? So we'll have what? So this is going to be a u plus iv. And then what's u plus iv cubed, right? Flip it over here. U plus iv cubed is u cubed. And then we'll have a minus iv cubed. And then I'll have a plus 3u squared iv. And then a minus 3uv squared, like so, right? I've just done the binomial theorem over here. So we have two terms. So and then we're going to have what? Then we're going to have a, so plus what? So minus a third of this expression, right? And it's going to write the real part of it out, right? So the real part's going to be what? It's going to be a u cubed minus 3 uv squared, right? Plus dot, dot, dot. The next term over here is going to be what? It's going to be an I, and then a u plus iv, and then plus what? Plus zeta cubed is going to be a plus 1, and that's zeta cubed over 3, of course, right? Over 3. And plus 1/3. And then what are the imaginary parts of zeta cubed over here? Zeta cubed over 3. The imaginary parts are going to be a u squared, 3u squared v, and then minus v cubed. Those are the imaginary parts, plus dot, 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 plus irrelevance, right? And then the last entry over here is going to be what? Just going to be, the real part of that thing is just going to be u squared minus v squared, right? Beautiful. So let's compute the real part and see what we're going to get. So, of course, times, yeah, that's beautiful. And so now what we're going to get is we're going to have a u, so this is 1/2. And do I have a 1/2 here? So probably my 1/2 of my parameterization doesn't need to be there, but it's going to work out fine anyway. This is going to be 1/2, okay? 1/2 of what? The real part's going to be u minus u cubed. So it's going to be a u minus u cubed. And then a plus what? Plus u cubed over 3, of course, u cubed over 3. And then plus uv squared. uv squared like this, comma what? Comma, the imaginary part of this thing is going to be a what? The imaginary part, or the real part of this thing is going to be that's going to be a negative v. And then this thing over here is going to be a, so let's see, what do we have over here? So I want the so these are the imaginary terms. So these terms go over here, get an I, right? So I have to put an I over here, right? Those terms have an I, and so I have to do the negative of everything over here, right? Good. And so the real, the imaginary part of these expressions over here with I plus 1 plus zeta is going to be a, let's see, think carefully over here. So we'll have a negative v, we'll have a positive v cubed over what? Then we'll have a positive v cubed over 3, right? So that's going to be a v, negative v, plus what? Negative v plus a v cubed over what? Then a minus v cubed over 3, right? So positive v cubed over 3, v cubed over 3. Then finally what? And then finally this is going to be also a negative. So let's see, these things have real, so I need to be a little more careful about this action, so let's be a little more careful so I get the right parameterization. So let's go over here. So these terms over here are I times these things, right? So I have I times everything over here. So let's rewrite this expression over here. So I think we made a little mistake. So let's erase this expression. The last term is correct, right? So let's do this carefully. So we have I times what? We have I times zeta, which is u plus iv, like that. And then we're going to have a what? Then we're going to have a plus zeta cubed, so I need the terms that have no i's over here, right? So it's going to be a, the real part. So I want to have the terms that have i's. So I have a minus I v cubed, and then a plus 3u squared iv, like that, plus irrelevant now. And then the last entry over here, the last entry is going to be a u squared minus v squared plus 2i uv. And you can be the real part of that thing over there. Excellent. Okay, so like we said, that first term is now correct. I have the real parts over here. Now I have to look at the real parts over here. So the real parts over here are going to be a I times this v over here, right? And so that's going to give me a, that's going to give me a what? That's going to be a negative v. Good. And then we have this I is going to be positive v cubed over 3. V cubed over 3. And there's a root in front of this thing over here too, right? So all this is over 3. Okay, so that's a positive v cubed over 3. Good. And then the last term over here is going to be an I times I, so that's going to be a negative over here. So the negative of what? The negative of this expression, which is going to be a u squared v, like so. And then a u squared minus v squared, like that. Beautiful. And up to a factor of a half, this exactly defines the Enneper surface, right? So this is my Enneper surface. Okay. And this expression over here, this way that we parameterize a minimal surface, this is called my Weierstrass-Enneper Parameterization. So this parameterization is called the parameterization of Weierstrass-Enneper parameterization of a minimal surface. Thank you very much.